Let f be a function from the set of positive integers to the set of positive integers. Suppose that f of n plus 1 is greater than f of n and f of n equals 3n for all n in the set of positive integers. Find f of 1992 and f of 2022. This video contains the following sections. Reading the problem carefully and understanding it. Developing a plan to solve it. Solving the problem. Thinking about it further and try to apply the approach to other problems. Near the end of the video, there's an additional question which can be solved using a similar approach to that used for solving the specific problem. If you find these helpful, please subscribe to the channel for notification of new videos by pressing the video watermark in the right-hand corner of the video player. F of n is an unknown function, but we know some of its properties. It's a strictly increasing function defined on the set of positive integers, and f of n equals 3n. According to the properties of the function, we can work out f of 1, f of 2, f of 3, and so on. For example, as f is a function mapping positive integers into positive integers, so f of 1 is greater than or equal to 1. Then we'll deduce the patterns of the values of f of n and find f of 1992 and f of 2022. Because f of 1 is in the set of positive integers, so f of 1 is greater than or equal to 1. Because f of 1 equals 3, so f of 1 doesn't equal 1. Otherwise, 3 equals f of 1 equals f of 1 equals 1, which is false. So f of 1 is greater than or equal to 2. Because f of n plus 1 is greater than f of n. So f of 2 is greater than f of 1, which is greater than or equal to 2. That is, f of 2 is greater than 2. Similarly, f of 3 is greater than f of 2, which is greater than or equal to 3. That is, f of 3 is greater than 3. And so on. We have f of n is greater than n. Now, we can conclude that f of 1 equals 2. Otherwise, suppose f of 1 equals k. K is greater than or equal to 3. Then we have f of 1 equals 3. This contradicts 1, as according to 1, f of k is greater than k is greater than or equal to 3. That is, f of k is greater than 3. So f of 1 must be 2, because f of 1 equals 2. So f of 2 equals f of 1 equals 3 times 1 equals 3. Similarly, f of 3 equals f of 2 equals 3 times 2 equals 6. F of 6 equals f of 3 equals 3 times 3 equals 9. Because f of n plus 1 is greater than f of n, so f of 4 must be 7, and f of 5 must be 8. F of 7 equals f of 4 equals 3 times 4 equals 12. F of 8 equals f of 5 equals 3 times 5 equals 15. F of 9 equals f of 6 equals 3 times 6 equals 18. f of 12 equals f of 7 equals 3 times 7 equals 21. So f of 10 must be 19 and f of 11 must be 20. So far, we have the graph of the function f listed in this table for the first 12 integers. When n equals 1, f of n equals 2. When n equals 2, f of n equals 3, and so on. Now, we can prove that f of 3 to the power of n equals 2 times 3 to the power of n. For n equals 1, we have f of 3 equals 6 equals 2 times 3. Suppose that f of 3 to the power of n equals 2 times 3 to the power of n holds true for n equals k. That is, f of 3 to the power of k equals 2 times 3 to the power of k. Then we want to prove f of 3 to the power of k plus 1 equals 2 times 3 to the power of k plus 1. Let f of n equal b. So f of n equals f of b. Because f of n equals 3n. So 3n equals f of b. F of 3n equals f of b equals 3b equals 3 f of n. F of 3 to the power of k plus 1 can be written as f of 3 times 3 to the power of k, which is equal to 3f of 3 to the power of k equals 3 times 2 times 3 to the power of k, which can be written as 2 times 3 to the power of k plus 1. So f of 3 to the power of n equals 2 times 3 to the power of n holds true for all n in the set of positive integers. So f of 2 times 3 to the power of n equals f of 3 to the power of n equals 3 times 3 to the power of n, which is equal to 3 to the power of n plus 1. So when a is in the closed interval 3 to the power of n, 2 times 3 to the power of n, f of a is in the closed interval 2 times 3 to the power of n, 3 times 3 to the power of n. Because f of n plus 1 is greater than f of n, and both a and f of a have 3 to the power of n plus 1 values. So f of 3 to the power of n plus n equals 2 times 3 to the power of n plus n. 0 is less than or equal to n is less than or equal to 3 to the power of n. Next, we can prove that f of 2 times 3 to the power of n plus n equals 3 to the power of n plus 1 plus 3n. 0 is less than or equal to n is less than or equal to 3 to the power of n. Because f of 2 times 3 to the power of n equals 3 to the power of n plus 1, and f of 3 to the power of n plus 1 equals f of 2 times 3 to the power of n equals 3 times 2 times 3 to the power of n, which can be written as 2 times 3 to the power of n plus 1. So for a in the closed interval 2 times 3 to the power of n, 3 times 3 to the power of n, there exists b such that a equals f of b equals 2 times 3 to the power of n plus m, where b equals 3 to the power of n plus m. 0 is less than or equal to n is less than or equal to 3 to the power of n. So f of a equals f of b equals 3 times b equals 3 times 3 to the power of n plus n equals 3 to the power of n plus 1 plus 3n. So f of 2 times 3 to the power of n plus n equals f of a equals 3 to the power of n plus 1 plus 3n. 0 is less than or equal to n is less than or equal to 3 to the power of n. Because 1992 can be written as 2 times 3 to the power of 6 plus 534. So f of 1992 equals f of 2 times 3 to the power of 6 plus 534 equals 3 to the power of 7 plus 3 times 534. Simplifying this, we have 2,187 plus 1,602, which is equal to 3,789. Because 2022 can be written as 2 times 3 to the power of 6 plus 564. So f of 2022 equals f of 2 times 3 to the power of 6 plus 564 equals 3 to the power of 7 plus 3 times 564. Simplifying this, we have 2,187 plus 1,692. Which is equal to 3,879. Think about the thought process for the previous question further and try to apply the approach to other problems, such as this one. A function f is defined for all positive integers and satisfies f of 1 equals 1,996 and f of 1 plus f of 2 plus so on plus f of n equals n squared f of n for all n greater than 1. Calculate the exact value of f of 1996. You can write your answers in the comments section if you like. If you have any mathematics questions of interest, you can write these in the comments section if you like. Thank you for watching. Hope you found this video helpful. See you next time.